So welcome to our review or introduction of DSC interpretation. And just to remind you, DSC, differential scanning calorimetry, we are measuring the heat flow into a sample. And your basic signals are, in the DSC, are going to be heat flowing into or out of the specimen as a function of temperature. So you scan the temperature and you measure how much heat is going into the sample or how much is coming out. And our normal convention is negative or endo heat flow. Flow into the sample is downward on the graph, and exo or heat out of the sample is upwards on the graph, and 0 would be no net heat flow. And so what we're going to find is that as we scan a sample, we get a number of signals. So the first signal of interest is simply a step change. And so let's plot one out here. And when you get this step change, this is associated in polymers with the glass transition temperature of the material. Now the TG can really tell you a couple of things, but the two things that can happen with the signal are that it can change in size or it can change in location. So if it changes in size, first scan, say large, and the second scan is small, the size change means that the amount of material that we're detecting the TG for has changed. So for example, a polymer that has a lot of amorphous material on a first run gives it a large TG, and then if it is treated in such a way that that amorphous material is reduced, the second run you may see a smaller TG. So this is basically going to represent a change in the amount of amorphous material. At least the amorphous material that is giving you that particular glass transition temperature. The other thing the TG can do is it can move, and so we can change location. So you have a couple of possibilities here. And again, this is always heat on the vertical axis, temperature on the horizontal axis. And so if first run, let's say, gives me a TG here, so we can mark glass transition temperature 1. On a second run, if that TG moves, this means we have this. We would call this a shift in TG, and it means you have a change in the mobility of molecules. Remember, the glass transition temperature is a measure of the ability of the molecules to dance, to move. And so if something changes in the environment that makes it more difficult for them to move, that's going to cause the TG to shift to a higher temperature. And if something changes in the polymer or the environment that makes it easier for them to move, that's going to shift the TG to lower temperatures. Now, a TG shift can show up either in the second run. It also could show up if I continued the run and then cooled. And so if we cool the run, the shift will show up in an inverse signal. So rather than dropping this way on the cool down, it's going to flip, be mirrored. So either of those things will produce then the TG shift. So there's my TG2. And that tells you that something has changed in the neighborhood so that molecular motions are more difficult if the TG shifted higher and are easier if the TG is shifted lower. Okay, so that is the glass transition or step change in the material. The other two signals are peaks, and the first of these is an exotherm. So exotherm, meaning out of, or heat flow out of the sample. And so there's a couple of things these can mean. But let's look at the first of these. Is we have a peak upward, and this means heat is being released. So usually my 0 would be there. You can literally have net heat flow out of the sample, not just a decrease in the heat required to warm the sample up, but actually heat flow, or heat being released. So we would say heat is released from the sample, in an exotherm. Now, it can be released because of conformational energy, that is, the molecules are arranging themselves into a lower energy configuration and their excess energy is released, or it can be heat released because of a chemical reaction. So let's start with heat released due to conformational energy, in this case crystallization. So if this is a crystallization peak, there's a couple of characteristics that we are going to see. What's happening in crystallization? If we had a microscope and we could look at the molecules, at low temperature, the molecules are just randomly oriented. As you go through the crystallization, the microscope view is going to change because this ordering of the molecules releases energy. We pick up that peak, but we're turning this into a crystalline structure. Okay. So we have now crystallized, or we have a semi-crystalline material, amorphous or only partly crystallized, further crystallization occurring. And then if we continue this run, we're going to have an endotherm out here. All right, and this will be crystal melting. And if we look at the microscope here, we once again have random molecules, and there's no order at all that's involved. So we'll come back and talk about this endotherm and crystal melting in a little bit. So an exotherm can be a crystallization, that is, the molecules were disordered and they acquire order. In the process of going from disordered to crystallized, they release their excess free energy because they're no longer in a random configuration. And we pick up that as heat flow out of the sample. The other possibility for an exotherm is a chemical reaction. And so oftentimes these also are going to go positive in terms of heat flow. And in this case, we're talking about chemical reaction or a cure. And there's no following endotherm associated with this change. And if you want to kind of visualize what's happening, we have at low temperature a bunch of, let's say this is a thermoset, we have a bunch of molecular segments here. And then at high temperature, those molecular segments have now connected by chemical reactions, primary bonds that have formed to form a network out of them. Okay, so chemical reactions creates a tighter network in the system. Now, obviously, if I go through this process, we're binding the molecules to each other. If we were to cool the sample down and run it again, we should see a change in the glass transition temperature. Okay, so that's exotherms. With endotherms and exotherms, the area under this curve, we could integrate this, or we can add this up with a numerical technique. Okay, these areas are the energy involved. Okay, so this is the heat released in the process. Okay. To keep the sample warming up, we would just have gone along the baseline. That is the energy flow necessary to warm the sample up. So everything above that baseline is energy that was released by the sample due to this phase transformation. The opposite of an exotherm is an endotherm. Endo meaning into, and so this is heat flow into the sample. And the signal is always going to be a downward peak, like this. And so again, heat flow into the sample, and we can integrate this area again, and that area is the energy required for this transformation. And this is energy flowing in to generate a phase change. So we're causing a change in the phase of the material. The phase changes that are possible would be crystalline to amorphous, so this is melting, could be occurring. You could have a liquid in the sample that's going to a vapor, and so this is the heat of vaporization that you learned about in chemistry. And you could obviously have solid going to liquid, which you did this in your metal, or you will do this in the lab in the metal samples as you melt them. So what are some of the possible variations that we're going to see here? Well, if we're talking semicrystalline polymers, let's focus on that for the moment. There's a couple of possible variations of the signal. You could have multiple peaks. And the simplest way to think about multiple peaks is that they're essentially an overlay of two peaks, melting peaks. And this mostly is because we have two different crystal morphologies is the most common result or cause of this. So you may have the row nucleated, remember the shish kebab structure, and you may have the spherolytic structure where all the crystallites are roughly symmetric, right? And so either one of these. This is has a lot of defects. None of the crystals are very perfect, so this is a high energy crystal structure, which means it's going to melt more easily, and it'll show up usually as the lower melting peak. This is a highly ordered, close to perfect. These are semicrystalline, so they can't be perfect, but this is as close as you're going to get. So it's going to melt at a higher temperature, and will show as the peak at a higher temperature. You may see two separate peaks, and then the question, two very, very different peaks. And so then the question here becomes, what is this? Is this two different materials, or is this something else? Okay. So the possibility here is I have two very different types of crystal structures. And the question would be, how could we tell if what we're dealing with is two different materials or one material that just has two different crystal structures? And the key is going to be your second run. So is this two crystal structures, same material, or is this two different materials? All right, so there's your question. Two different materials, two different crystal structures. If we do a second run, and let's redraw this so we can do this a little bigger. So in your first run, you had the two peaks. When we run it a second time, there's a couple of possibilities. It could just retrace, and so if it retraces, then you're let's say slow cool between the first runs. So first run is in black, slow cool in red. In our second run, and if we get a dashed line, then basically we know we had two materials that crystallize in different fashions. All right, so you may have a copolymer or a blend of two semicrystalline materials that actually have separate kind of melting behavior. So this would be two different polymers, and they may be blocks on a copolymer, or they may be a blend. All right. However, if on our second run we end up with, let's say blue here, baseline is the same, and the second peak gets a whole lot bigger, then what's that saying is that we had one kind of molecule, and the first time it was in two morphologies. One melted at a low temperature, one at a high. When we slow cooled, it all crystallized into the most stable crystal formation, and so the peak got significantly larger on the second run, and so the blue area now is much larger than the black area from the first run. Okay, and so we would say the area blue is larger than the black area. Okay. Why? Because we have one molecule, one type of molecule, and this time they all crystallize in the same morphology. The other possible endotherm is vaporization, and that's a phase change again, but now it's from a liquid to a gas, and you're going to see again a peak. And the key here is we'll have this peak, and on rerun, so it would be your first run in black, if we cool this down slowly and we rerun it, if that just disappears in the second run, okay, then this was a volatile, something that evaporated and is no longer there. If you were to cool and it was a volatile and you just continued the run and did the cooling cycle, what you'll find is nothing happens on the cool down because the volatile is no longer there. It can't interact. Now, if this had been a melt, then on cool down you would have recrystallized, and so you get an exotherm. That's the crystallization exotherm on cool down. So you can always distinguish a volatile endotherm because it doesn't reappear. In this case, it just disappears completely. And in this case, we know this was not a volatile because this energy got dumped into the peak, the melting peak of the later curve. And so this area increased, and therefore this energy didn't disappear, it just shifted to a higher temperature. So we melted a more stable crystal. All right, now all of this stuff interacts, and so let's look at an example of an interacting plot here. So your volatiles may affect the polymer's behavior. So let's say we do our first run and we get a TG, and then we get an endotherm. We could continue this as a loop, so let's do that. Let's continue this as a loop. And this is one option when you run your experiment, to just loop and do a controlled cool. And so here's my cooling going on there. Now, the fact that we have an endotherm followed by nothing on the cool down, there's no exotherm, no crystallization, says this was a volatile. So we can label that. And this highlights a point. I think a lot of times students want to quickly say, well, this is a thermoplastic or thermoset, this is semicrystalline, this is amorphous. And what you really want to do is work from what you can tell about the state of the polymer back to what type of polymer it is. So you first identify what's going on here. So this is a volatile because it doesn't reoccur. I have a TG on the heat up, and it shifts on the cool down. So I've had a TG shift, TG1, and there's my TG2. They're no longer the same. So something altered the neighborhood, okay? So what would cause a TG shift? Well, we've had to, if the TG shifted to a higher value, that means that mobility became more difficult. So what could leave and make mobility more difficult? How about a plasticizer? So this volatile was a plasticizer, and we see the evidence of that because when we remove it, the TG of the polymer shifted, okay? So you know these things about the state. The polymer, when you received it, had a volatile in it. That volatile was acting as a plasticizer. Now this plasticizer might be intentional. It may be an additive in there on purpose, but it could be water, it could be alcohol, something that was absorbed from the environment that will act as a plasticizer, and that'll show up. You'll pick up that TG shift in the DSC when that happens. Now, we could also stop at this point and cool the sample and rerun it. On the second run, if we do the second run in blue, so let's stop and cool, we'll see, say same kind of behavior, but again, the TG will shift, and then this will follow out to a line. So this would be a second run after cooling, and we'll get the same TG. The TG2 is going to be the same as we would get on the cool down. But again, the endotherm doesn't repeat because that was a volatile. The TG shifts because it was a plasticizer. Now, you could have a volatile that doesn't affect the TG. There's no requirement that anything volatile present affects the TG at all. Your sample wasn't surface dry. You could have polyethylene that doesn't absorb water significantly. Could show water here, but it doesn't affect the TG or anything else significantly. Now, the DSC is tremendously sensitive. It is able to pick up very, very small changes. So let's talk about an extreme case of this. And the reason we commonly do 2 runs, students will bring me a DSC curve, and they'll say, oh, I think there's a TG here, but look at this. The baseline isn't flat. It's all wiggly. There's all kinds of weird stuff going on. And so, again, always heat and temperature. I've been skipping these, but you know they're on every one of these graphs. So let's say we have a first run that shows a TG, and then it shows a bunch of other stuff, wiggly stuff, and then maybe trails off down here. And so there's your first run. And you go, oh, that's ugly. I don't know if something's happening here. So let's do a slow cool. And let's run it again. And on our second run, we end up with this beautiful baseline. Nothing's happening. Okay. And so you say, well, this is an amorphous material. I got a TG. I don't see melting. I don't see crystallization. I don't know if this is a thermoset or thermoplastic from the graph, right? All we know is I got a TG. So I have predominantly amorphous behavior. The TG size didn't change from the first run to the second run, so we didn't alter the amount of amorphous material or anything. But we have this weird baseline that's misbehaving. Understand that this instrument is able to detect conformational energy of the molecules. Crystalline conformation is a big energy generator. But if you had a microscope that would let you see the molecules, going into the first run, you could have literally had conformational energy. This could be a thermoset where you have cross-links locking these molecules together. There's some kind of connection in them. And the molecules are kind of stretched. Some of them are not in low energy conformations. And by heating them up, we allow them to fold back on themselves a little bit. They're not going to crystallize. They can't do that. But they may assume a more regular kind of conformation. And the bond energies are minimized because they assume a low energy conformation. And so what's happened is on your first run, you have converted from this kind of strained molecular orientation to a fully relaxed minimum energy arrangement. And that's what's going on in all of these bumps and peaks and whatever that you're seeing on the baseline. So a messy DSC sometimes is difficult to interpret, which is why we usually will run things twice. Even if we don't think there's been going to be any change in the key signals, in this case the TG, a lot of times the noise that's generated by the stretched molecules and other things goes away and things get a lot clearer. So what should you be able to tell from a DSC? And on your quizzes and exams, you'll always be asked to figure out these things. What kind of polymer is it? So we would call these type, amorphous, semicrystalline, thermoplastic, and thermoset. And you've got to know what all these are, right? They all relate to the structure of the polymer. And then there's a bunch of state variables that we've obviously just been talking about, and you'll need to be able to identify which of these are operative. Incomplete cure. And of course, an incomplete cure, incomplete chemical reaction tells you you have a thermoset. Incomplete crystallization. You've got to distinguish that exotherm from the cure. We've talked about how to do that. But if you have crystallization present, you know that you're dealing with a thermoplastic that's semicrystalline, because that's where you're going to find crystals. Obviously, we've talked about a volatile, something that evaporates, liquid to gas, phase change. You could have a volatile that's a plasticizer. Any other kind of plasticizer you're not going to be able to detect in the DSC. If it doesn't leave, it's there, it's permanent, you're not going to pick it up. So it's not going to be a question you have to answer on exams. We could have multiple polymers or monomers. In a block copolymer, it's possible that you would have more than one TG show. And we'll look at that in a second. And you could have multiple crystal morphologies, which we talked about at some length. All right, I want to emphasize again two things. In general, it is best to answer the questions about state first. Do these first. Those are the signals. That's what's going on in the polymer. And then next, from those, what can you do? What can you tell about what kind of polymer it is? Okay? Now watch out for two things. If you see crystallization anywhere in the polymer, there is no way it's a thermoset. Thermosets do not crystallize, not in the cured state. They may crystallize, the monomers may crystallize in the pure state before you mix in hardeners, but as they harden, as you cross-link them, there's no way they can crystallize. So if I ever see crystallization and thermosets showing up in the same answer, it's not even partial credit. Those are incompatible. The other thing is to remember, as we talked about already, that you can see something as amorphous, but that doesn't necessarily tell you if it's a thermoset or thermoplastic. Now, if you know it's amorphous and you're not sure if it's a thermoset or thermoplastic, from the signal because you didn't see a cure, you did not see any signal, right? And really the cure is the only signal you've got that would distinguish. Then what you might want to do is open the cell and look at the sample, because if it's a thermoplastic, it's going to be a puddle, and if it's a thermoset, it's maybe changed color, but it's not going to change shape. So if you're not given that information, if you can't look at the sample, an amorphous polymer could be either thermoset or thermoplastic, lacking a signal, curing signal or something like that. That's all you're going to be looking at. All right, so I think that's most of what we need for DSCs, and hope this helps.